Hello, business calculus students. Today we will talk about section 3.4, which has to do with absolute maximums and minimums of functions. This is the first material on homework 9 and quiz 9, which also will include section 3.5. This homework and quiz will open on Monday, March the 30th, and will be due on Sunday, April the 5th at 11:59 p.m. So let's get started. As I said, this section has to do with finding absolute maxes and mins of functions. We call this optimization section. So just to kind of give you a graphical idea of what absolute maximums and minimums are, so far we have talked about relative maxes and relative mins, which are these turning points like we have here and here. An absolute maximum and minimum are the true largest value of a function and the true smallest value of a function. So in this case, both the absolute minimum and one of the relative minimums occur at this point where x is equal to c sub 1. There's only one absolute maximum for this function, and it occurs actually at the end of the interval from a to b at the x value of b. So we can have relative maxes that are, or relative minimums that are not our absolute maxes and mins, and we can also have these special absolute maxes that might be the same thing or might be something different. This is a little bit confusing kind of as it stands right here, but no, maxes are still at the top and minimums are still at the bottom. So the rest of this down here, it says, just notice that the absolute maximum and or minimum can actually occur at the end point of whatever our interval is. So that's going to occur occasionally. So we'll get to those when we run into some problems. All right, so this is the extreme value theorem, and it basically just guarantees that if we have a closed interval, and we'll talk about what happens when it's open a little bit later on, but if we have a closed interval, then we were guaranteed that we will have at least an absolute maximum and an absolute minimum value. May not have relative maximums or minimums, but that's okay. We are guaranteed to have an absolute maximum value and an absolute minimum value. Keeping in mind, again, our relative extrema are going to be those turning points, okay? Our absolute extrema may not be turning points. So to find the absolute maximum and minimum value on a closed interval, the first thing we do is the same thing we've done before, is we find the first derivative. We'll find the critical values from the first derivative by setting the derivative equal to 0 and making sure that any of those x values are actually on the interval from a to b. And then we'll take those values and the endpoints, and we're going to actually plug them into the function to see which gives us the largest value and the smallest value. So we will really truly be looking for the largest value of the function and the smallest value of the function based on those critical values and then the endpoints that were given for the interval. So let's start by just looking at a graph here. It says, according to the U.S. Department of Energy, a vehicle's fuel economy in miles per gallon decreases significantly at speeds over 60 miles per hour. And I'm going to try to make this graph a little bit larger. Okay, this is speed in miles per hour. Sorry about that. Okay, so the first part says, estimate the speed at which the absolute maximum fuel economy is obtained. So here's my fuel economy, and we're looking for the largest fuel economy, which looks like about 30 miles per gallon. So somewhere in here between the 50 and 55 mile per hour range. So I would probably say an estimate would be the maximum fuel economy is obtained at a speed of 55 miles per hour. So somewhere about in here, looks like it kind of flattens out, but we're going to go with that. Okay, so and then it says estimate the speed at which the absolute minimum fuel economy is obtained. And that's over here. This is the smallest value of the function, and this is obtained at a speed of 5 miles per hour. So that very slow speed of 5 miles per hour is going to get you terrible fuel economy. But about 55 miles per hour, according to this graph, we're going to have pretty good fuel economy. You go too fast, your fuel economy definitely goes down. So the last part of this says, what is the fuel economy obtained at 70 miles per hour? So we're really kind of looking at reading graphs here. So here is my speed, or my miles per hour. I'll kind of pull this up a little bit here. So this is my miles per hour, and at 70 miles per hour, it looks like here is my point, and so my Y value here is 25, and so it looks like my fuel economy is 25 miles per gallon. All right, so right in here about that 55 mile an hour range is a great speed for you to be driving. Okay. So this next question has to do with, I think I need to move my picture up a little bit, finding the absolute maximum minimums over this indicated interval for this given function. So notice that this is a linear function because it's x to the first power. So this is going to be a straight line. Remember, straight lines do not turn, so there won't be any relative maximum or relative minimum value. But we're going to go through this same process. You probably have a pretty good idea of what's happening here. We'll explore that also. So the first step in this process is to find that first derivative. So we're going to find the derivative of this function. So let's go find f prime. Okay. And as we find f prime, we get 2. This is a constant. This is a positive constant. If you hadn't already figured it out that this was a slope, this line has a slope of positive 2, which means it's a strictly increasing line. The first derivative being positive also tells us that this is a function which increases everywhere. So because there's no x values in our first derivative, there are no critical values from this first derivative that we're going to find. And since we have no critical values, then we're simply going to evaluate. If you go back here to this process, there weren't any critical values, and we're going to take critical values and then the endpoints of the interval and evaluate the function at those values. So moving back over here, so we have an x value of -1 and an x value of +1. So since we have no critical values, we need to find f of -1, and then we need to find f of +1. So f of -1, we're going to have 2 times -1 plus 4, which gives us -2 plus 4, so we get a value of +2. Now we're going to do exactly the same thing at f of 2. I hope you have an idea of whether this is going to be larger or smaller, but we'll plug it in and see. 2 times 1 plus 4 gives me 2 plus 4, which gives me a value of 6. This is the largest value produced in this function, and this is the smallest value produced in this function using my 2 endpoints. So we can say that based on this, the absolute, so we're going to make the distinction here, the absolute minimum value of this function is 2, and it occurs, so occurring at x is equal to -1. So we're going to make this nice statement here. And then we can say that the absolute maximum value of this function, maximum value, is 6, and it is occurring at x is equal to +1. So be really careful here. These still occur at the x values, but the minimum and maximum values are the actual y values. Now you probably should have guessed this, that this is the graph of a function, so I'm just going to give you a little bit of extra information here. You may or may not want this, but you're going to get it anyway, so you can just ignore it if you'd like to. So my y-intercept is here at 4, and I have a slope of 2/1, so it's going to look something like this. This is a very kind of terrible looking picture here, but notice that my graph continues to go up. So at -1, it's going to have the smallest value possible in this interval, and at +1, it's going to have the largest value. So if I only look at this portion of my graph from -1 to +1, here is the largest value, and here's the smallest value. So that kind of makes sense. Lines are pretty easy, pretty nice, and pretty friendly. Okay, let's move on to a nonlinear function. So same thing we're going to do again. So the first thing we're going to do is we're going to find the first derivative. So we're finding f prime. This is a pretty nice function again. It is a polynomial function. It is quadratic. You should know what's going to happen with this one. So my derivative is 2x minus 6. To find the critical values, I take 2x minus 6 and I set this equal to 0 and I get x is equal to positive 3. Now, this is my critical value, and I look at this critical value and I check, is it between -1 and positive 5? And the answer is yes, it is. So since it's between those two numbers, now I want to evaluate f of -1. I like to do them in order. I want to evaluate f of 3, and I want to evaluate f of 5. So I want to find the value of the function excuse me, at both endpoints and at the critical value. So for this one, I'm going to have -1 squared. Make sure you're squaring that negative. 6 times -1 minus 3. We'll go through this process. 1 plus 6 minus 3. So it looks like I'm going to have 7 minus 3, which is going to give me a value of 4. So 4 is the value at -1. We're going to do the same thing here for 3. So 3 squared minus 6 times 3. Minus 3, so I'm going to have 9 minus 18 minus 3. So it looks like -9 minus 3 is going to give me a value of -12. So far that's the smallest one, and it's going to occur at 3. And then finally here we have 5 squared minus 6 times 5 minus 3. And so I'm going to have 25 minus 30 minus 3, so that looks like -5 minus 3, and that's going to give me -8. -12 is the smallest value, and -1 is the largest value. So my endpoint of 5 really doesn't have any effect here, and that's not terribly surprising. We should have expected our critical value. This is a quadratic function. It opens up. It is going to have it's going to have a minimum at the critical value of 3. -1 is my endpoint. Sorry about that. So at 3, we're going to have our not only our absolute maximum, but it is also our relative maximum. And then minimum, sorry, my brain is very tired, and then our absolute maximum is going to be at 4. So let's write that out so I can write it and not say it. So our absolute, so this is our absolute minimum value is -12, and it occurs at x is equal to 3. And now let's see if I can write this one correctly. This is my absolute maximum value, abbreviating here, is 4, and it occurs at x is equal to -1. As I said, this is the x value that was my critical value. I should expect it to give me a relative max or min. In this case, because my function opens up, it's going to give me that relative minimum. But right now I'm looking for my absolutes. So my absolute minimum value is -12, occurring at 3, and my absolute maximum value is 4, and it's occurring at -1. This is just a nice ordered pair, but it's neither a max or a min. All right. Next, cubic function, not quite as easy just to guess at, so let's go through the process here. So our first derivative, so we're going to again find that first derivative. Finding f prime of this function is going to be 3x squared plus 2 times 1/2 is just 1, so plus x minus 2. So this one's a little bit messier, but it's not going to be insurmountable. So my critical values, I'm going to take 3x squared plus x minus 2 and set this equal to 0. Hopefully this is going to factor nicely, otherwise you guys are going to get to watch me play with the quadratic formula, but I think this one's going to factor pretty nicely for me. Looks like I want 2 and 1 and positive and negative. This gives me -2 at the end, and a 3x minus 2x gives me x in the middle. So if I take 3x minus 2 and set that equal to 0, and x plus 1 and set this equal to 0, this one's nice, it gives me -1, and this one gives me a positive 2/3 if I add 2 to both sides and divide by 3. Okay, and y'all are going, oh yuck, it's a fraction, that's nasty. Now let's check. Are both of our critical values on this interval from -2 to 0? And the answer is no, they are not. X is equal to 2/3 is not in the closed interval. So even if it would have given me a relative max or min, I don't care because it's not in the closed interval, so I'm not going to use it. So the only values I'm going to use are -1, -2, and 0. So that means I need to find f of -2, I need to find f of -1, and I need to find f of 0. So we're going to go about plugging these in. So this is going to be -2 to the 3rd power plus 1/2 times -2 squared minus 2 times -2 plus 4. This looks like it's going to be -8. That's going to be 4 times 1/2 or plus 2, and then plus 4. Negative and negative give me a positive, and then plus 4 again. And so this is actually going to turn out to have a value of positive 2. So at -2, I have a y value of positive 2. Let's see what happens with -1. So I have -1 to the 3rd power plus 1/2 times -1 squared minus 2 times -1 plus 4, which is going to give me -1 plus 1/2 plus 2 plus 4. So this is going to be 6 minus 1 is going to be 5. Looks like we have 5.5. I probably did some arithmetic wrong there somewhere, but hopefully we're good. Okay, and then the last one is going to be 0 cubed plus 1/2 times 0 squared minus 2 times 0 plus 4. All of these terms disappear, and I have a y value of 4. And these are my values here. So, all right, so this is our largest value, this is our smallest value, and at x is equal to 0, we just have a very nice value of 4. So notice that my absolute minimum does not have to be negative. So we say that the absolute minimum value is 2, and it occurs at x is equal to -2, and the absolute maximum value is 5.5, and it occurs at x is equal to -1. If they want this as a decimal, you can write this as 5.5, or you can write it as a improper fraction. So 5.5 is the same thing as 11/2, 2 times 5 plus 1, and it's also the same thing as 5.5. You just kind of have to read the directions. Okay? All right, moving on to the next question. We kind of like these. These aren't so bad. Here's another quadratic. This one's opening down. Maybe you recognize some things going on here, but let's find that first derivative. So we find f prime of x in this case. This is going to be 6 minus 6x. So again, we're finding those critical values. Only one of them because I have a linear derivative here. So this is going to be -6x is equal to -6, giving you this extra step in here. X is equal to 1. Is 1 between 0 and 4? The answer is yes. So I am going to use this critical value. So I need to now find f of 0, f of 1, and f of 4. Notice I'm just going back to that original function each time. So f of 0, I'm going to have 1 plus 6 times 0 minus 3 times 0 squared. Those all disappear, and I simply have this nice y value of 1. For f of 1, I'm going to have 1 plus 6 times 1 minus 3 times 1 squared. So I'm going to have 7 minus 3. Looks like a y value of 4. So far, that's the largest. And then we're going to have 1 plus 6 times 4 minus 3 times 4 squared, and this is going to be 1 plus 24 minus 3 times 16. So it looks like I'm going to have 25 minus 48, which is going to give me negative 23, which is by far the smallest one. Remember, this graph is opening down, so it shouldn't terribly surprise me. My largest value here is 4, so here is my absolute maximum value is 4, and it occurs at x is equal to 1, and the absolute minimum value is negative 23, and it occurs at x is equal to 4. So there we go, one more problem. Okay. So now this is a 4th degree polynomial, so it could have several things going on, but we are just looking at this closed interval from negative 2 to 2. So same thing one more time, just giving you another example, a little bit larger polynomial in terms of degree. So this is going to be 4x to the 3rd power minus 6x squared. When I take this to find my critical values by setting 4x to the 3rd minus 6x squared equal to 0. I can factor out a 2x to the 2nd. That's going to leave me with a 2x minus 3, and that's what I'm going to set equal to 0. I get 2x squared is equal to 0, and I have 2x minus 3 is equal to 0. This gives me a critical value of 0, and this gives me a critical value of 3/2. So if I add 3 to both sides and divide by 2, both 0 and 3/2 are on this interval from negative 2 to 2. Thinking about this as a number line, is 0 between negative 2 and 2? Is 3/2 between negative 2 and 2? The answer is yes to both of those. So now we're going to find f of negative 2. I'm going to do them in the order that they come, f of 0, then I'm going to do f of 3/2, and then finally I will do f of positive 2. So for this first part, negative 2 to the 4th power minus 2 times negative 2 cubed. So this is going to give me a positive 16. This is going to be a negative 8 times this negative 2. So plus 16, so this is going to give me a value of 32. F of 0 is going to be 0 to the 4th power, 0 times 3, so this is going to give me a y value of 0. So these are my y values so far. 3/2, we'll come back and do that last. So let's do 2 to the 4th power minus 2 times 2 to the 3rd power. This is going to be 16 minus 16, which also gives me a value of 0. And now we're going to do this one. So let's see if we can do this without having to pull out our calculator. If we have to pull it out, we just have to pull it out. So 3/2 to the 3rd power. Let's see if I can get the right exponents here. So this is going to be 81 over 16, 3 to the 4th power, 2 to the 4th power, minus 2 times 27 over 8. I'm trying to not cheat and use my calculator here. Minus, this is actually going to simplify to 27/4. Okay. So 81/16 minus a little bit of fancy footwork here. Probably going to pull out the calculator. I'll cheat just a little bit. 27 times 4, so that's going to be 108 over 16. And that gives me negative 27 over 16. What a lovely number there. Okay. So I'm pretty sure I haven't made any mistakes. It would be very nice if that was the smallest value, but I don't think it is. It's okay. So this is my smallest value, and this is my largest value. So here is my absolute max of 32 at x is equal to -2, and this is my absolute minimum value, is this -27/16, and it occurs at 3/2. You shouldn't be terribly surprised to find at least one of your critical values is going to produce for you either a maximum or a minimum. All right, I think we have two more problems. This one is a little bit special because notice it's not a closed interval. So if we do not have a closed interval, then we're simply going to work with what we've done before, which is our relative maxes and mins. So we're going to find the derivative of this. I'm going to actually rewrite this to begin with because remember this is x squared plus, and I'm going to rewrite this as 432x to the -1st power. It just makes it a little bit nicer to find the derivative. So the derivative is going to be 2x minus 432x to the -2nd. And so I'm going to rewrite this as 2x minus 432 over x squared. This is what I'm going to set equal to 0 to find my critical values. So this one we have to be really careful with setting it equal to 0. So I'm going to add that to both sides. So I have 2x is equal to 432 over x squared. I'm going to multiply both sides by x squared, and so I get 2x to the 3rd power is equal to 432. And I'm going to divide both sides by 2, and I'm going to get x cubed is equal to 216. And I bet if we take the cubed root of 216, we find that we get 6. So the cubed root of 216 is 6. So x is going to be equal to, and it's not a plus and minus, it's just a 6. Is 6 on the interval from 0 to infinity? Yes, it actually is. So we can check, in this case, we don't have to check the end point of 0. We simply need to find out what's happening at x is equal to 6. So we can either put this on a number line, our first derivative number line, or if you recall, we can actually use our second derivative to find this out. So let's go ahead and find the second derivative of this function, which is going to be 2. We're going to go right here, and then it's going to be plus, and this is going to be kind of a large number. So it looks like 864 x to the -3rd power, which is going to be 2 plus 864 over x to the 3rd power. If I were to plug this critical value of 6 in here, it doesn't really matter what number I get, but this is going to be a positive value. So since it is a positive value, that tells me that the function is concave up at a critical value, which means that at x is equal to 6, I am going to have a relative minimum. Remember, if we did our number line test, it would go down and then up. And since I am looking though for absolute, then this relative minimum is actually going to be my absolute minimum is going to occur at x is equal to 6. Now, what is that minimum value? Well, the minimum value, how do we find it? We take that x value and we plug it back into the original function. So we need to find f of 6. So we're going to have 6 squared, or 36, plus 432 divided by 6. That should be a pretty nice number. I just don't know it off the top of my head. So if I divide that, 72. And so 108 is the minimum value at x is equal to 6. All right, one last problem in this set. So an employee's monthly productivity, M, in the number of units produced is found to be a function of time, the number of years of employment. For a certain product, a productivity function is given by this function here. For T is 0 to 40 years. 40 years of employment, I guess they usually figure you retire. Time is not going to be less than 0. So we want to find the maximum productivity and the year in which it is achieved. So we are going to find the derivative. So we start with the first derivative of this function, which is going to be negative 4t plus 100. And so we're going to find the critical value for this. So 4t plus 100 is going to be equal to 0. And so negative 4t is equal to negative 100. And t is equal to 25. So based on this, now we have our two endpoints. So we want to find m of 0, 25 is between these two, m of 25, and m of 40. And so we're going to plug this in. You might have an idea what's happening here because we're only looking for the maximum, but because we're doing this, we're going to plug in all of these, but you might recognize what this function is. So 2 times 0 squared plus 100 times 0 plus 180. So this value is going to be 180. So this is the units produced is 180. So we're going to do the same thing when we plug in 25. So 100, times 25 plus 180. And this is going to give us 1,430. And then finally when we plug 40 in, so we have 40 squared plus 100 times 40 plus 180. This is going to give us, inside of our calculator, 980. So the most productivity, the most units produced is 1,430, and that happens at year 25. So after 25 years of employment, then for this particular company, the maximum productivity is achieved. So we could say that after 25 years of employment, the maximum productivity of 1,430 units is achieved. So practical application problem. All right, well, that is the end of this particular section. This, again, is section 3.4, and look forward to you tuning in to the next section. Goodbye.